When we talk about functions of more than one dimension, one of the important things we should define and have a look at is how do we take limits of such functions. We've seen that if you have a function f of x, just depending on one variable, the way you do it to take a limit when x goes to some value a is you would write limit when x goes to a of f of x. And this meant that sometimes we write it with brackets, other times we don't, but the brackets are always there, even when we don't write them, until we take the limit and then the operator is gone. Now when we look at the function that depends on two variables, f of x, y, and that many times we will refer as z, and z being a surface. We're also going to have a look at how these functions look like. We want to also have a similar way to calculate limits. Of course, if the function depends on two variables, then we should be explicit about the limit we're calculating, which means that we need to specify which value x is tending to and which value y is tending to. Let's say that you want to calculate a limit when x goes to a and y goes to b. In this case, for functions of two variables, you would write the limit when x, y go to a, b. This is a point in two dimensions of f, x, y, and again, these brackets are kind of always there even when you don't write it. And in an ideal case, you can then calculate a specific value. If you can remember from section 3 when we talked about limits, for this limit to exist, a condition had to be fulfilled. Essentially, the limit when x goes to a from lower values of f of x had to be the same as the limit when x goes to a from slightly higher values of f of x. This was the condition for this to exist. What you could probably now ask is there a similar condition that we can apply to functions of more than one variable to know that the limit exists? The answer is yes, but it's complicated, very complicated. Why is it complicated? That is because you can literally approach point AB from an infinite number of ways. Say you have this curve, the lecture notes on section 7.2, which is what we're covering. You can think of this actually as a surface, essentially something that given x, y coordinates, the z is giving you the value of a function. And in principle, you could try to calculate what is the limit when x and y coordinates tend to, for example, this point. And in a way, to show that the limit exists, you'd have to calculate it from every single direction. There's essentially an infinite number of ways you can take curled paths, straight paths, incline and non-incline, which means it is incredibly difficult to prove that a limit exists. But if you also remember from section 3, we've defined what a continuous function is. A continuous function had to satisfy those three conditions, if you remember. The function had to be defined at that point, the limit had to exist, and also the limit equaled the value of the function at the point. And if you look at these lecture notes at specifically this point here, and I'm changing the curve all the time, so this function is changing, but go along with it. If you look at it, you'll see that it is continuous. There is no gap or a hole in the fabric of space-time of the lecture notes, which means that the function is continuous. So in many cases, provided that you know that a surface or a function with any number of dimensions is continuous at that point, calculating the limit is also as easy as for functions of one dimension. All you have to do is plug in the values and you get it. So let's start with the simplest case possible. For that, let's clear the space for these functions that only depend on one variable. And let's go with the function that you can see in your lecture notes on section 7.2. This is the function that you have there. And what we're going to try to do is to calculate the limit when x, y go to 5, 1 of xy over x plus y. Again, this is about taking the limit. This is the limit operator, which is being applied on the entire expression. And remember, here we could also write this as z. Z is a function of x and y. Y in this case is now a variable. For this case, let's assume that you know that the function is continuous at point x, y equals 5, 1. If it is continuous, then this implies that the limit is equal to the value of the function at that point. So all you have to do is to plug in the values. In this case, you get 5 over 6. Therefore, calculating a limit of a function of more than one variable can be incredibly easy. You also have this example showing you this function. So this is f of x, y, which is given by xy divided by x plus y, and also what is happening in the vicinity of point xy equals 5, 1, and why the limit is just a value of the function at that point. That is because the function is very nicely behaved. It is continuous. You don't really see any hole or gap. In reality though, many times we do not know whether a function is continuous or not, and therefore showing that the limit exists and calculating it is actually not that straightforward. But what we'll see next is actually it's much easier to show that a limit does not exist than to show that it does. And to show that a limit doesn't exist, all you have to do is take a limit along different paths and show that you get different values. This is the equivalent of showing for a function of one variable that if you take the limit for values lower than that value, you get something. And if you take the limit for values higher than that, you get something else. If the values do not agree, the limit does not exist. In this case, for functions of more than one dimensions, you apply the same technique, but instead of picking values which are just below and above, you can actually take lines or relations between x and y to specify a direction. And if they're different, they don't exist. And we're going to show a practical example in the next video.